active. The slope tells you we have a higher mineralization rate of your particulate matter, and the increased rate of oxygen utilization rate. The interesting thing which I forgot to mention is the bottom curve, the control curve, was done at a dissolved oxygen concentration of between 1 and 3 milligrams per liter, which is typical of a system. Ours was operated, it's actually 2 and 5, sorry, and ours was operated between 0.5 and 1.5, which is typically we would consider as being stressed. Anything under 2 milligrams per liter dissolved oxygen, you have a problem, especially with nitrification. Okay, and then the shorter cycle time, so we can do the same job in a smaller reactor. This is the performance curve we got out of little pilot plant we did with Sasol. Sasol is a big company in South Africa, petrochemical company, where they start off with a COD of approximately 20 to 30,000, and they had a typical performance of about 85 up to 90%. Interestingly enough, they added micronutrients before we started. So the average performance is less than 85%, which is normal if you consider you're trying to break it down from 20,000 to as low as possible. This COD was about 4,000 or 5,000 milligrams per liter. COD as chrome. We only use chrome. Okay? As soon as the RQO are introduced, the performance increases to more than 95%. Fortunately, the system was stressed. It did not have sufficient oxygen. The sludge yield decreased. The sludge yield being the kilogram of sludge produced per kilogram of COD removed. And it dropped from about 0.2 to 0.05, which was a close to 70% reduction in sludge production. And the simple reason for that is if a system is under stress, you're producing the acids. The acids are food for archaea under low dissolved oxygen concentrations, and they are removed, in other words, as methane, and you don't produce excess biomass. We then did a full-scale trial on the same wastewater, and we had exactly the same results. The COD came down dramatically from about 5,000 to, I think in the end we dropped it to less than 2,000. The suspended solids, one of their concerns, main problems they have is suspended solids carried out of the activated sludge reactor. We lowered that from about 3,000 to 400. And the sludge production was reduced once again from about 0.2 to 0.05, basically confirming what we've achieved in the lab. This is rather interesting. An activated sludge system, if you do the numbers, in the way I do it is the modified or UCT model. You can calculate based on the volumes you want to treat, the amount of COD you have to remove, how big a reactor you need. That's a given for a certain sludge age. So you can draw up these curves, and this was done for a reactor that is supposed to treat 20 megaliters a day, which is 20 tons, more 20,000 tons, and then operated at certain mixed liquor concentrations. This was the straight line is the actual basin size. Okay, it's less than 2,000 cubic meters, less than 2 megaliters. So the residence time in this basin is approximately 2 hours. So if you want any nitrification to happen, you would require to run extremely high mixed liquor concentrations. As you can see, to get underneath this straight line, you need to run at about 6,500 mixed liquor, total solids concentration. But that will end you or give you only a 10-day sludge age. And if you want any nitrification to happen, you would require it to be almost at 15 days sludge age. That's straight theory. They, on the other hand, were running the plant at 3,500 milligrams per liter, and they were not achieving any nitrification. So we were asked, could we achieve nitrification on that plant? And yes, we did. This is typically the ammonia out of their reactor, which is about 20 milligrams per liter as it comes in. It goes straight out, no nitrification. And as soon as we started, as you can see, the archaea are established in the system, and here ammonia concentration drops. Similarly, COD concentration is improved. And the bottom one is suspended solids. We dropped that to less than 10, which is basically negligible amount of suspended solids getting out of your clarifier. Once again, we had to convince them to reduce their sludge wasting rate to allow us to contain a lot of mixed liquor in the system. And so once again, we confirmed what we saw at the petrochemical plant. We're reducing sludge production by at least 50%, dropping it from 0.3 approximately to less than 0.2. That means you have 50% less sludge you would have to dispose of. Biofilm processes work on the same principle. The biofilm processes have this advantage that you automatically have an anaerobic section in your biofilm, because oxygen only penetrates about 150, maximum 300 micron. So if your film thickness is a 500 micron, maybe 1 millimeter, the rest is all anaerobic. So your substrate goes all the way in, but not your oxygen. And in the biofilm system, the main problem is always its oxygen. Looking at biofilters, this is the trickling filter you saw the photograph of. The bottom curve is typical what you will find in the literature, and it's been confirmed on numerous studies, that if you increase your organic loading to a trickling filter, your removal goes down. If you want about a 90% removal, your loading should not be higher than about 250 grams of COD per cubic meter. As you increase the loading, it slows down to approximately 50% COD removal. The rest just goes out. It cannot consume that. You don't have enough oxygen. Whereas in an archaea system, we have a 90% removal all the way from 250 all the way to 1.5 kilos of COD per cubic meter. That is substantial. That means you've increased the capability of your trickling filter by 500%. Looking at nitrification, nitrification is the same. What happens is, if you want complete nitrification, you would need to load your system about 200-250 grams per cubic meter. If you want to remove sufficient ammonia. As you increase your loading, your nitrification drops to virtually zero, because they cannot compete for oxygen with the COD consumers. Their growth rate is too slow. With archaea, we are way above what the theory predicts we should be able to get. We get about 50-60% ammonia removal